good morning, or good afternoon, or good evening, I don't know. Welcome to my course on Diophantine Geometry. And welcome to this CIMPA school. I think that this is the first course you are following, the first course that was planned for this school. So the topic I'm going to talk about is Diophantine Geometry. Oh, but maybe I should introduce myself first. So my name is Elisa Lorenzo García. I work at the Université de Neuchâtel in Switzerland. And I participated already in some CIMPA schools, like 3. This is my 4th, actually. So, I hope you're going to enjoy this course. So, about this course, here I brought like the index, so the different topics we are going to visit during this week, or, well, the time it takes to you. This format is weird, right? I guess at that moment, maybe you are used to these online courses, but actually for me, it's the first one that I kind of do in this way. So, yeah, let's see how it works. Okay, so for today, the first thing that we are going to discuss is the definition of absolute values, and we are going to present the product formula. So this is for today, for the course of today. So in the next course, this is my planning. These are all the things I want to tell you. So for the next one, we'll talk about heights in projective space. Then we are going to talk, this course, lesson 3 is kind of an introductory lesson in the sense that I'm going to recall some things that maybe some of you already know, maybe some of you don't know. So I think that is good that I explain those things just to be at the same level. So about curves and about abelian varieties. So this is going to be useful. This is going to allow me to introduce the Néron-Tate height associated to an abelian variety. Then I'll talk about the famous Mordell-Weil theorem. So we'll kind of give a proof, you will see. We'll also see Falting's theorem. So maybe some of you already know this is a very famous theorem. The proof here is very, very complicated. But we'll try to show like some of the details of the proof, how it works. And then, well, these 2 points, I'm going to talk about them the same day, during the same course. And until here, let's say that I'm going to try to give you like all the proofs, all the references, everything. But the last day, I'm going to allow myself to talk about some open problems and some research directions. Like, I don't know, maybe in the future you want to work on it. I don't know. So, okay, so this is about the topics I'm going to explain. And so let me tell you a little bit about the references. So I'm going to put my notes. So I prepared some notes and with some exercises. So you can find all this material in the platform online, in the online platform for the course. But I want to say something about the notes because really the course, the things I'm going to tell you, they are classical things, which means that actually many people wrote about these things and tried to do like perfect notes for this course. So I'm not reinventing the things, I'm just explaining to you like what is known and the classical results. So I'm mainly following this book. So this book is by Marc-André and Joseph Silverman. So this is going to be like the main reference. So it's André and Silverman book. So I'm not writing down the title is the same thing of the course, right? Diophantine Geometry. So I'm not writing it. So you are going to find the exact reference in the notes that I'm going to put online. So this book, and then I'm really following another book. So I don't have that book right now physically with me, but they are quite classical books, let's say. So I think that you can really find them in a library easily. I don't know. Well, contact me if you have problems to get the books. Otherwise, you can just follow the notes I prepared that are going to be online. So it's Bombieri and Gabler. So this is the second book. So again, I have my notes. So the notes are going to be online. But they are not really my notes. Like, I feel bad saying that they are my notes. I'm really following the books. So, in each section of the notes that corresponds to each of the points that you have here, I'm really like following like some parts of the book. This book, André Silverman, or the other book, Bombieri-Gubler. okay? So yeah, let's start with the course for today. So the course for today is about absolute values and the product formula. So I'm just going to start like with some definitions, really just to check that we are all at the same level and that we all have the same background. So in this case, I'm going to be also very precise about which parts of the books I'm following. So I'm basically following section B1 in the André Silverman book, okay? And then, you can also find this, if you prefer, sections 1.214 in the Bombieri-Gabler book. So, in case you want to double check if there is something that is not clear, of course you can ask me if there is something that you don't understand, but maybe you just want to reread things again in a different way. So, you can look at any of those references. Okay? So, let me start, as I said, with some definitions, some background. So, let's start, for instance, what is a number field? So, definitions. So, I'm just going to give here like a list of definitions that, I think mostly all of them you know, but again, just to be clear. So, the first thing that we are going to work with are number fields. So, what is a number field? A number field, K, is just a finite extension of the rationals. Finite extension, right? This is a number field. So what is now an algebraic number? So maybe I should say about number fields, so you know that number fields, they can be always described like something like this. So Q, the rationals, and I add another element. So this is because of the primitive element theorem that tells you that any number field is actually generated by one element. Of course, this element is going to be what is called an algebraic number, right? And what is an algebraic number in general? It is a root of a polynomial that I'm going to write like this. So you just take a polynomial, and because I let here a coefficient, right? So I want rational coefficients, but because I'm letting here have a coefficient, I can ask them to be integer. So basically an algebraic number is a root of a polynomial in this way, where the AI are integer numbers. Right? And we say that alpha is actually not only an algebraic number, but an algebraic integer if an is equal to 1. Okay? If we can find such a polynomial that is monic, with the first coefficient equal to 1. Right? In particular, so I can give like an example. Given a number field, K, we denote its ring of integers by OK. So, what is this? Those are the elements in K such that alpha is an algebraic integer. Okay, so this I think you are familiar with, but again, just in case, I'm repeating. What else is important here? Okay, so in general, we can have like finite extensions of number fields, right? So we can have an extension like this. When we have an extension like this, it may happen that it is not Galois, right? Recall that Galois means that actually all the conjugate numbers of all the elements here in L, they are in L, okay? This is the meaning of Galois. We can take, so given such an extension, we can look for the Galois closure, right? And I mean, it's not always a standard, but so this is an extension of number field. And we can denote by L-gal, L-k, the Galois closure. What is the Galois closure? Actually, it's the smallest number field that you can find in such a way that this extension is Galois and it contains L, right? So I mean, I really think that you know about Galois theory, but just to be clear, okay? Okay, so maybe I can give like a small example, right? About like some extensions, because I mean, we are going to use them. We are going to do examples with them later, right? So I'm going to do some examples. And I mean, we are going to compute like valuations for those examples later. Okay. So example, we can take, for instance, K to be this biquadratic extension, right? So in this case, this extension, it is Galois over Q, right? And I mean, it's easy to compute in this case the Galois group, right? Who is the Galois group? The Galois group is the set of morphisms, field morphisms from K to K that fix the base field, the rationals, right? So, I mean, in this case, this is actually generated by two elements. Let me call them tau 1 and tau 2. So, tau 1 is the one that sends I to minus I and square root of 3 to square root of 3, and tau 2 is the element that leaves I fixed this time, but sends a square root of 3 to minus the square root of 3. So, I mean, this group is actually isomorphic to the cyclic group of order 2 times the cyclic group of order 2 that is called the Klein group, right? And the four elements that we have are those two elements that they are order 2 elements. They commute. And I mean the product, then you have the product and you have the identity, and those are the four elements that you have in this group. So this is an example, but we can also consider an example. So I take this, I call it again K, but it's a different one. I'm going to call it to be Q of alpha, where alpha is a root of the following polynomial. So for instance, this number field is not Galois. So it is a number field of degree 3, because I mean it's generated by one element that satisfies, is the root of a degree 3 reducible polynomial. So I mean this is a extension of degree 3, but it is not Galois. If you want it to be Galois, you have to add like all the conjugate numbers to alpha, right? And in this case, we get that the Galois closure of this extension is actually equal to Q of alpha, and you need to add a square root of minus 23. Where is this minus 23 coming from? Actually, this minus 23 is the discriminant of this polynomial, so it's the thing that we have to add. And I mean, in this case, we can check that the Galois field associated to this extension is isomorphic to the symmetric group with 6 elements. So, I mean, those are your examples. I mean, I really think that you know about them. So, I mean, it's just to refresh a little bit the concept we are going to manipulate. And, okay, after this small introduction of concepts, I can really start with Diophantine geometry. Because you are following this course on Diophantine geometry, but maybe you don't know what is Diophantine geometry. So, I mean, if you were here in person, so, I mean, I would ask to you, so what is Diophantine geometry? What is for you Diophantine geometry? And I mean, maybe someone has an idea, but now nobody can answer, so I have to answer myself to these questions. So, I mean, I don't know, I guess that maybe the thing that sounds familiar to you is this word, well, I mean, of course, geometry, you know what is geometry, but Diophantine. And I mean, when you hear the word Diophantine, the thing that you think about is Diophantine equations, right? I mean, it's to try to find the solutions to some equations with integer coefficients. And I mean, this is what we are going to do, more or less, in the sense that, I mean, Diophantine geometry takes care about solutions, but I mean, solutions to equations, at the end, you can interpret this as rational points on algebraic varieties, right? So, I mean, in one lecture, I'm going to give again the definitions of algebraic varieties and all that, in case you don't remember very well. And this is idea, Diophantine geometry, we are going to care about the rational points, or small points, and I'm going to define what is the meaning of small. So, small points on varieties, on curves, on like solutions to equations, to systems of equations. So, I mean, this is what Diophantine geometry takes care to try to solve those equations. And I mean, the tools that Diophantine geometry use are, well, what I'm going to define today, that they are valuations. So this is like the most basic ingredient. And then in the next lecture, by using those valuations, we are going to use like the main tool in Diophantine, well, or one of the main tools in Diophantine geometry, that they are the height. What is the height of a point? Or what is the height of a number? And I mean, somehow those heights are going to be useful to measure when a point is small and when it is big. So I mean, this is the meaning when I said before, like small points. So we are going to use those heights. Okay, very well, so let's start with the definitions. So I'm going to erase here. So this was like a pre-introduction, let's say, the concept that I recalled now. And now I'm really going to go to the topics of this course. So let's go with the first definition, that is the definition of what it is an absolute value. So, I mean, I guess that you can think, hey, I know what is an absolute value. Yeah, but we are going to generalize that concept of absolute value that you know. Okay, so definition. An absolute value on a field K is a function that we denote like this from K to 0 infinity. Okay, so it goes to the real, to the non-negative reals. So I mean, this is like the notation for the usual absolute value, right, that you know. Such that, so we ask this function to satisfy some conditions, and these conditions have names. So, I mean, the first condition, I write the condition and then I give the name, is that the absolute value of an element is equal to 0 if and only if x is equal to 0, okay? And I mean, this property is called to be non-degenerate. Okay, this is the first property. The second property that we ask is that it is multiplicative, meaning that the absolute value of a product is equal to the product of the absolute value. So this is being multiplicative. Right? The third condition that we know, so I mean you are kind of familiar with those conditions, right? Is the triangle inequality that you know. So I mean, for the product, here we get the equality. For the sum, we don't exactly get the sum, but we get at least one direction, right? We get that this is always smaller or equal than this sum. So this is a triangle inequality. So, I mean, we have only, an absolute value only have to satisfy these three conditions, But now I'm going to give you a fourth condition that if it is satisfied, then it receives a special name, this absolute value. This absolute value is said to be non-Archimedean if the following holds, the fourth condition, that is that actually we can go further, and it's not only that in the triangle inequality we have this direction, so that we can say something even more precise, and is that this value is smaller or equal than the maximum of these two values. So this property is called the Ultrametric inequality. And in case it is satisfied, we say that the absolute value is a non-Archimedean absolute value. When this condition is not satisfied, then we say that the absolute value is an Archimedean absolute value. So we remove the non-Archimedean. Okay, so let's see an example, because I mean, actually, I guess that when I was giving this definition, you had in mind the typical example that you were thinking on the rationals and you were thinking on the absolute value, the classical normal standard absolute value on the rational, and you were thinking if those properties were satisfied, right? And of course, they were. So let's do an example with the rationals. So, example. We are going to take K, so the field that we have in the definition. Actually, I mean, this definition is quite general. Like, I mean, I'm talking about a field K, so I'm not saying a number field. It's true that in practice, we are mostly going to work with number fields. But, I mean, this is totally general for any field. I didn't ask for any extra property. Okay, so now, in the example, we are going to take that field equal to the rationals, equal to Q, right? Then we have an example of an Archimedean absolute value, right? That is the one that you have in mind, the one I was thinking that I guess you were thinking about, right? That is to say, and I mean, we denote it, I mean, even if for you, you will denote it like this, like, because we are going to play with so many absolute values, so somehow we have to make a distinction. So I'm going to call it like this, okay? So it's the infinite absolute value. And I mean, this, you know, I mean, is the thing that you know, is the maximum between x and minus x, okay? Okay, you know this one, and maybe, I don't know, you are also already familiar with those ones, non-Archimedean, absolute values, that they are the p-adic absolute values. So, I mean, if you know about p-adic numbers, I'm going to do a small example with p-adic numbers later. But actually, if you don't know about p-adic numbers, don't worry, it's not a big thing. It's better if you know about it, because, I mean, it's like a source of examples. But if you don't know about them, you are not familiar with them, it's not a big deal, so don't worry. So the example that we have here is that we start by writing, I mean, in order to define the absolute value associated to the non-Archimedean absolute value associated to a prime P, the first thing that I need to do is to write X, an element for the one I want to define the absolute value, in the following way. So I write it as a power of P that actually to the exponent that is the order of X at P. So I mean, this is the power of P that divides X times A divided by B, and such that A and B are integers, but there is no P on them. So P doesn't divide the product. So, I mean, I can write this in a unique way. So, I mean, in a unique way, I mean that, I mean, this order, this exponent here is well defined, and I mean, there is only one option for this. Then A and B, I can get different things, right? Because if I find an A and a B that work, I can multiply A and B by 7, let's say, if 7 is not the prime I'm looking at, okay? Because I still need to have this condition. Okay, so once that I write x in this way, how do I define this absolute value? So I define it in this way. So I write a p here to make the distinction between the one that I have there. And now I do the definition. This is equal to p 2 minus the order of p of x. Okay, so keep this in mind. This is the definition, and this is very important. So basically, what does it mean? So two numbers are close p-adically if there is a big power of p that divides the difference. Why? Because, I mean, we are defining the absolute value that somehow is the distance, right? I mean, if you want to look at the distance of two numbers, you are going to look at this, right? This is the p-adic distance. So you are going to get that those two numbers are close. So when they are close, with the distance, it's small. But when are you going to get that this number is small? Because here we have p to the minus something. Actually, what you want is this thing to be very big. And this thing being very big means that there is a big power of p. So this is the order of p of x in p at p. You want a big power of p dividing this. So, I mean, in this case, the difference of two numbers. So, I mean, this is a little bit weird, right? I mean, it's not, so, I mean, of course, this you know, right? I mean, we start with those absolute values, so we can define distances like this, and then we have a topology. And, I mean, the thing is that the p-adic topology in the rationals, I mean, is not intuitive in the way that is not the Euclidean distance, that is the one that we have in mind. And this Euclidean distance is the one that is coming from here, from the Archimedean absolute value, right? I mean, this is this is for us, like, this is closer to this than to this, right? This is clear. But with the p-adic distance, this is not what we have in mind. So two numbers, again, I repeat, they are close if there is a big power of p that divides the difference, okay? This is the idea. Okay, so I'm going to give a couple of more definitions that we need, so about this absolute value, because, I mean, of course, the idea we are going to see is that all those are all the possibilities up to equivalence, so I have to give the definition of equivalence. So all those are all the possibilities for absolute values for the rational numbers. And somehow, thanks to this, we are going to be able to define or to characterize all absolute values for number fields. Okay, so I need to define this equivalence, right? So I'm going to give you the definition. So two absolute values are equivalent. Sorry, I'm going to put this in a box. If they define the same topology. So what is the topology I'm talking about? Again, when we have an absolute value, we can define a distance, and as I did here, and once that you have a distance, then you have a topology. You can define who are the open sets, right? I mean, the balls are the open sets. So a base for the open sets. So, I mean, this defines a topology. So now you're going to say that the two absolute values are equivalent if they induced the same topology. But of course, I mean, in general, this is complicated to check, let's say. So, I mean, we have another characterization of this. So this I'm not giving the proof. Why I'm not giving the proof? Because somehow, I mean, this I assume that you saw it, like maybe in a functional analysis course or a topology course that you followed in the past. So, I mean, if you are not familiar with this, like, don't hesitate to contact me, and I can send you, like, maybe some references to check this. So, okay, now, two absolute values are equivalent if they define the same topology, and actually this is equivalent to say that this norm So this absolute value, the second absolute value you are considering, so these two means the second, we have two, one with a 1 and one with a 2. So the one with a 2 is actually equal to the one with a 1, but I allow here an exponent. Yeah, if this is equal to this for some s greater than 0. Okay? So, I mean, somehow what this means is that I gave you like several examples here of absolute values, but I mean, nothing is not forbidden to get here, for instance, a 2, right? Like you could say, okay, instead of defining it like this, I'm going to define it as P2 minus twice the order of x at P. You could have done that. And then you would obtain something, I mean an absolute value here, that according to the definition of equivalent, it's equivalent. So, I mean, you are not interested on equivalent things, right? You just want it for its equivalence class. Okay, very well. So this is the definition of equivalent. So now a little bit more of definition. I mean, I'm going to, because it's a small one, I'm just going to use this a small square in the blackboard. So we are going to call MK the set of absolute values up to equivalence with the definition that we just gave. So, I mean, I'm going to state it later as a theorem, but actually MQ, so Q the rational numbers, is equal to all the absolute values that I presented here. So those ones are the non-Archimedean ones, so we have one for each prime number P, and this one is the Archimedean one, that we have only one. We'll see examples, I mean, of other fields for which we have more Archimedean absolute values. Okay, and we denote by MK infinity the subset of MK of Archimedean values, and MK0 the set of non-Archimedean values. Okay, so why? Because, I mean, now when we are going to do like computations with those values, actually we have to distinguish both families because they have slightly different properties. And why do they have these slightly different properties? Because of this, because this fourth condition that we saw here, right? I mean, this is going to make things a little bit different for two cases, but not a problem. Okay, so another definition with this, don't worry, we're going to do a lot of examples later. So, I mean, well, I don't know, it's my opinion. I think that even if I give you the definition, well, for me, when I learn a new definition, until I don't see an example, I cannot really like understand what is happening behind. So don't worry that I'm going to do like several examples. Okay, so another concept that is related with those absolute values, so there is the concept of evaluation, okay? So given an absolute value, so now I'm going to use the notation I just defined here, okay? So the set of absolute values, we can define a valuation. So, I mean, this I know that is a little bit confusing. So we have an absolute value, and associated to an absolute value, there is something that is called a valuation. And actually, we are going to be mixing all the time absolute values and valuations. So it's going to be a little bit an abuse of notation. But I mean, I hope that is going to be clear when we mean an absolute value and when we mean a valuation. So, I mean, if you want, with the examples that we just did here, I'm going to give the definition, right? But I mean, this is the absolute value, and the order that we define here is the valuation. So, I mean, somehow this is so this we did it for the rational numbers, and we want to do it like in general. Like, given an absolute value, how do we get the associated thing here, like the order This is what we are going to call the valuation. And now to make even things a little bit more difficult, like in some places, I mean, I'm going to call it valuation, but you can find it, I mean, if you look at the literature, you look at other books or papers or even Wikipedia. So, I mean, sometimes a valuation is called a place. So be careful, it's exactly the same thing. Okay, so the way of we can define a valuation in the following way. So this is going to be minus logarithm of x. So this minus logarithm of the absolute value, okay, the absolute value is the one that we fix here, I mean, is really the absolute value that we had here. Okay, so I mean, we are really trying with that equation, the minus logarithm, we are really trying to recover the order that appears here. Okay, and now is when we have the abuse of notation, because sometimes what we are going to do is that by abuse of notation, we write sometimes B in here. I mean, this is the set of the absolute values up to equivalence. And this is a valuation associated to one of the absolute values. But sometimes, because it's easier, we just write it in this way. So, I mean, be careful with that. I'll try to be precise. But, I mean, sometimes you're going to see like a valuation that is in the set of absolute values. And, I mean, sometimes also what we do is that we start with the valuation, right? We start with B and we write the corresponding absolute value like this, right? So I mean, if you want, again, I go to the example that we had here. Here, this P is the valuation, right? Because it's the order at P. So we call the valuation at P. Well, I mean, I know that it's confusing because they are kind of the same thing and we are mixing them. But really, I mean, I hope to be clear enough when I do examples to see what I mean. Okay, so another definition now. So let's consider a field extension. So keep K prime over K be a field extension. We take a valuation. See, I'm doing the abuse of notation here. So I take a valuation for K and I take a valuation for the field extension for K prime, okay? Now we say that W divides B if W restricted to the field K is equal to B. So what I did here, so I mean, W is a valuation for K prime, but K prime is an extension of K, so K is inside K prime. So I mean, I can look at W restricted to K, and this gives me a valuation on K. So if this valuation happens to be V, then I say that W divides V. Okay, this is the notation. This is going to happen, I mean, now we are going to see like many examples when we have like a number field and we have like a p-adic valuation, so associated to a prime. So we have like primes that divide other primes. So I mean, this is related. I mean, I don't know if you already followed a course on algebraic number theory, but I mean, this is like the prime decomposition of ideals of K on K prime. Okay, and we're going to see more examples with that later. Okay. Now, in the special case, if K is a number field, we say that B is a p-adic valuation if B restricted to the rational numbers is equal to P. P, understanding P as the p-adic valuation, so the one that we saw there, as the order of P, okay? So in this case, we say that B is a p-adic valuation. So it may happen that we have several p-adic valuations. We'll see examples. Okay, so I mean, sorry, but always at the beginning, when you start a new topic, you have to give many definitions, right? Once that we have all the definitions, then we can start to give results. So another definition. A complexion of K with respect to the place B. Notice that I use the word place here. That is the same thing that valuation. So I mean, I'm trying to make you get used to the use of the different terminology for the same concept. Okay, so a complexion of K with respect to a place or a valuation B is an extension field that we denote like this. So it's not necessarily finite, it's just an extension field, okay, such that so is an extension field with a place W, and now such that, and I'm going to write in the other side the conditions that has to be satisfied. Okay, so, well, the first one is the natural condition you are thinking about when we have an extension and we have two valuations. So the first condition that we want is that the W divides B. Okay, again, meaning that the restriction of the valuation W here in KV restricted to K is equal to the valuation that we started with. Okay, that's the meaning of dividing. I'm recalling it. Okay, second condition, the topology of KV induced by W is complete. So, I mean, I don't know, I mean, I guess that you recall what is complete, but just in case I'm recalling, so complete means that all Cauchy sequences converge. So, I mean, again, we have a topology in K of V that is induced by this valuation, but I mean, this valuation gives you a distance, right, of two elements. So, I mean, the topology that we have here is a metric topology. It's given by a distance. And I mean, when we have a distance in a topology space, then we can talk about Cauchy sequences. So, I mean, Cauchy sequences are sequences that starting from some point, all the elements in the sequence are very close, right? So, I mean, here I'm not giving the definition. This is an analysis course that you follow in a first year bachelor. But I mean, I'm just recalling. So, I mean, all those are concepts that I'm assuming that you know. I'm just trying to recall them a little bit. So, I mean, a topology space or a metric space in which you have a distance is called complete when it happens that all Cauchy sequences converge. So, an example of this if you want. So, you can take the rationals. So, the rationals, they are not complete, right? Because you can get, for instance, a sequence of rational numbers getting close. I mean, which limit is a square root of 2? And a square root of 2 is not a rational number. So, this is a Cauchy sequence that doesn't converge, right? So, the rationals is not a complete metric space. However, the reals, they are, and actually this is the construction of the reals, right? I mean, I'm going back to this later, so I'm not saying anything else. But, I mean, this was just to refresh the concept of complete. Okay, and now the third condition that we need is that K is dense in KV. So what is the meaning here of being dense? Well, I mean, you know what is the meaning of being dense, right? I mean, being dense just means that for any open subset in KV, the intersection with K is not empty, right? I can write it. So for all U non-empty in KV open set, the intersection of U with K is non-empty. So this means that actually I'm getting something that is complete and such that the restriction of the valuation gives me the original valuation, but I don't want it to be so big. This is the meaning of being dense, or this is the meaning of asking for this condition, okay? And again, by abuse of notation, I mean, I'm very sorry, we are really abusing of the notation. By abuse of notation, we denote WU by V, okay? And now, if you want, after this definition, we can state the following theorem that actually is going to tell you that this complexion exists and it is unique. So, theorem, the complexion exists and it is unique. Well, up to isomorphism. Up to actually isometric isomorphism. So, I mean, this is why we can do this abuse of notation, because actually the complexion is completely determined by V. In particular, W is completely determined by V, because it is unique. Right. So this is why we do this abuse of notation. What about the proof? So, I mean, I'm not giving the proof, but I mean, I can give you like some ideas if you want. So, the proof is not complicated. It is long. And I mean, you can find it in the references, in the two references that I gave you, they say the same thing that I say. Oh, this proof is a classical thing, it's easy, I'm not giving it to you, but here you have some references. So, I mean, I'm doing the same thing. I'm telling you that you can look at the references in the books if you want. But I want to give you like some ideas. I mean, I don't want just to say, look at the references. So which ones are the ideas? But actually proof, so it's not the proof, but ideas, right? But is the same construction that you do to construct the reals from the rationals. So let me be a little bit more precise. So, I mean, actually there are like different ways of constructing the reals from the rationals. So, I mean, again, this I guess that is something that you have seen in a first year course of analysis. But I mean, the easiest, or I don't know if the easiest, but at least the most intuitive way of constructing the reals starting from the rationals is considering like Cauchy sequences, and then you look at the complexion. I mean, actually is what you do. What do? You take Q, you take the standard absolute value, so the first one that we define, the Archimedean absolute value of the rationals, so I mean given by the maximum of x and minus x. So you use this to define like a metric here on the rationals, and now what you do is that you consider the set of all Cauchy sequences up to equivalence, right? Because if you want all the Cauchy sequences to converge, somehow, if it does not converge, you have to add it, right? To get something that is complete. And so you consider all these Cauchy sequences up to equivalence. Up to equivalence means that two Cauchy sequences are considered to be equivalent if the difference converges to 0 of the two sequences. And I mean, you just consider, I mean, all these Cauchy sequences up to this equivalence, and I mean, these are the reals. This is a construction that you do for the reals. And it is complete, of course, because somehow you added, like manually, you added the limit of all Cauchy series. So it is complete. And I mean, of course, the inherent valuation that you get here is induced by the one that you have here. So when you do the restriction to Q, you get the same thing. So I mean, this first condition. And then this is also something that you see in this analysis course, that, for instance, the rationals are dense on the reals, right? So, I mean, basically the proof is the same one. You just have to, the proof that you have already seen for the construction of the reals is the same thing, but you just change the rationals by the field K that you have here, and you change the standard absolute value in the rationals by the valuation V you are working with there. And then you get exactly the same thing. Okay, so then we have this theorem. So now we'll see another theorem that actually tells you which ones are the Archimedean absolute values for the rationals. So I'm going to write it here. So theorem, this has a name, Ostrovsky. So again, this theorem is a big theorem. So, and again, sorry, not giving the proof, but I mean, you have a reference in the books that I'm giving to you. So, I mean, as I told you, this is a starting point, right? So I have to tell you like many definitions, big theorems, and then we can really start to work, to prove our results. So, I mean, I'm going to state this Ostrovsky theorem that actually tells you that the only complete Archimedean fields are the reals and the complex numbers. So, I mean, this is very strong. Because, I mean, that means that, I mean, if you have a field K and your field K has a valuation B that is Archimedean, then the complexion can only be the reals or the complex numbers, because those are the only ones complete Archimedean fields, the real and the complex numbers. So, I mean, this is very strong. That means that if you have a field that has an Archimedean value, it has to be a subfield of the reals or of the complex numbers. And even we can say more. I mean, we can prove the thing that we are using without proving all this time, that is about the Archimedean values of the rationals. So now imagine that I take again the field K to be the rationals, and I'm going to consider a non-Archimedean value. So I know one, right? The classical one is a non-Archimedean value. But actually, we can prove that it is the only one. Why it is the only one? Because, I mean, it has to happen that the complexion with respect to this Archimedean absolute value, okay, so the KB that we have here, it can only be the reals or the complex. So with the reals, I mean, we know that actually this is the complexion for the standard absolute value. So this gives us 1, okay. But now what's happening with the complex numbers? That actually the rationals, they are not dense on the complex numbers. So, I mean, this condition is not satisfied, right? The third one. Which means, in particular, that, I mean, C cannot be the complexion of any other absolute value, Archimedean one, for the rationals. Which means that actually there is only one Archimedean absolute value for the rationals. So, I mean, as a corollary of Ostrovsky theorem, we can state the following. Q has a unique Archimedean absolute value, and is the one that we know. Okay, so maybe it's the moment to do a small example before I go further. So, I mean, I'm going to do an example with the p-adic numbers. So, I mean, again, I hope that you have already seen p-adic numbers, because, I mean, it's good for all the examples with these things. But if you haven't, it's not a problem, okay? So you will see here the example. So, for instance, I'm going to take k equal to q3, so the three-adic numbers. So, I mean, recall that an element here actually can be described as following. So, indexes greater or equal than a fixed one to infinity of this, and where xn is in this set. In general, if you have qp, here you are going to have p to the n, and here the set is going to be 0, 1, 2, p minus 1, right? So, I mean, elements look like this. Here the valuation is 3, right? Q3 is already complete, because actually Q3 is the complexion of Q for the valuation 3. So, I mean, this is why I call it 3 again, the valuation that I have in Q3. I do this abuse of notation that I mentioned here. Okay, and how do numbers look like this? Like, what is it? So, I mean, they are written like this. Somehow you can look at them really as Cauchy series. So, what is the way of looking at those as a Cauchy series? Actually, what you do is like each term are the terms that you have here, but I mean, you make them finite. So you go all, so I can write it explicitly, maybe it's better. So I can define, this is like a capital X. This is equal to this. So if I write this like this, I mean, this is actually an integer, right? Because, I mean, this is a finite, well, a rational number, because n0 may be negative. So, I mean, this is a rational number, because it's a finite sum. And now with this, I can construct a Cauchy sequence. Why this is Cauchy? Because actually, I mean, those terms, when you do the difference, what you get are the last terms in the series. And each time you get something that even with the absolute value is big, right? Because we have here big powers of 3 when n is big, but actually p-adically, so three-adically, because p is equal to 3 in this case, you get a big power of 3 dividing the differences of two terms like this. And having a big power of 3 dividing those terms makes the distance small. So, I mean, those terms form a Cauchy sequence. Again, where the metric is the one given by the three-adic topology, so by the three-adic valuation. So, I mean, this Cauchy sequence is actually encoded, if you want, in this expression, in this way of writing it. And I mean, this is why the elements in Q3 looks like this. They are indeed Cauchy sequences. And I mean, and this is a complexion, because this is what we are doing, right? I mean, we are adding all Cauchy sequences of Q with respect to this three-adically valuation that give us a distance, a topology, and we are adding all those Cauchy sequences. So, I mean, this is precisely Q3, and this is a complexion, right? I mean, those are the definitions we already gave. Okay, so this is an example. Maybe just because it's funny, I mean, I'm not going to develop it more, but if you are not familiar with the p-adics, maybe you can try this as an exercise to convince yourself about how many things you have inside this or which kind of numbers you have there. So, I mean, for you to check, if you haven't seen it before, you can write 1/5, for instance, in a three-adic way as follows. So this is the notation to say that I'm working in base 3, right? And I mean, those numbers written like this means that in the sequence, the x something negative is equal to 0, because there is not a point. The x1 is equal to 2, the x2 is equal to 0, x3 equal to 1, x4 equal to 2, x5 equal to 1, and we follow. And this is periodic, so I mean, after these two, this term is periodic, and it goes to infinity. And I invite you to check that this is actually 1/5 with this triadic notation. Okay, so that was an example that was needed at some point, but now, I mean, I'm going further in the sense, okay, so we know which ones are all the valuations or all the absolute values for the rational numbers, right? I mean, we saw that the Archimedean ones are those ones, Q, for Q is like the classical one, the standard one, and then the non-Archimedean ones are the ones that they are coming by prime numbers, right? So the p-adic ones, so like in this example. But what happens in general when we have like a number field? Can we also characterize all the possibilities for all the absolute values? And actually we can, and I mean, I'm going to give the following proposition that actually describes those valuations. So, well, you will see. So, I mean, this proposition is going to be useful. We are going to be using it during all the course. Proposition, let K over Q be a number field. So I repeat, a finite extension of the rationals of degree n. N, and let me write n as follows, as R1 plus twice R2 with real embeddings row 1, row R1, and complex ones, tau 1, the conjugated one, to tau R2 and the conjugated one. So I go back now to the notation. So what is happening? If I have a number field of degree n, then I have n embeddings of K into the Galois closure. Okay, or if you want, I can write it here. So that means that I can see K into the algebraic closure of Q. There are n possibilities for the embeddings, right? So if you want to think about an example, you can think, for instance, Q of I, right? I mean the rationals, and I added I, square root of -1. So I can see Q of I into the Q bar. Q has to go to Q, but I can send it to I or to -I. So there are two embeddings, two different embeddings. So I mean, in general, when you have a degree n number field, you have n embeddings. Some of those embeddings are real ones, right? Like meaning that the image of K into Q bar is contained in the real numbers, so they are real ones. And some of them, they are complex ones, meaning that actually the image of K into the Q bar is not contained in the real. And in this case, what's happening is that given such an embedding, so for instance tau 1, you always have the conjugated one, so tau 1 bar. So somehow you can pair up, right, all the complex embeddings. So the number of total embeddings is equal to n, so it's equal to the real ones plus the complex ones. But the complex ones, I can pair up them in this way, and this is why we get 2 here, right? Okay, so this is only notation. This is still not what the proposition is saying, but just to check that we agree with the notation. Okay, So in this situation, then there is a bijection as follows. Here I get all the real embeddings and all the complex ones, but only one of them. So I know if I'm taking one, I don't take the conjugated one. Okay, it doesn't matter which one I take, but I only take one for each pair. So there is a bijection between this set and the Archimedean valuations. And it can be made explicit, where the idea is that we define the absolute value corresponding to a sigma, so sigma is one of the elements that we have here, is one embedding, to be equal to the standard absolute value. So I mean, this is the Euclidean, if you want, absolute value of sigma of x. Okay? So you define it in this way. So in this way, you have the going in this way. So like given such an embedding, you get a valuation by doing this. And I mean, actually the statement of the proposition, the claim is stronger, is that actually all the Archimedean valuations are obtained in this way. They come from such an embedding. Okay, so now let's go to the p-adic valuations. How do we construct them? So p-adic, or if you want, like the non-Archimedean ones, how do you get them? So for this, we start by factoring p. So we take p, a prime number in the rationals, and we are going to write down the factorization of this ideal. So I mean, I look at p as an ideal, and I look at the factorization in the ring of integers of k. I recall at the beginning what was the ring of integers. So this gives us something like this, right? I'm going to call it R or R. So let this be the factorization. Of the ideal P in OK, the ring of integers. Okay? Then there is a bijection between the different primes. So those are prime ideals. So the different prime ideals appearing in this factorization and the p-adic absolute values of k. So who are the p-adic absolute value of k? We gave the definition before. Basically are the elements in oops, sorry, this is a k. In mk0, because I'm looking at non-Archimedean ones, but that restricted to the rationals give me the valuation p, the p-adic valuation. So those are the p-adic absolute values. So basically, I mean, in this way we have described all the possibilities for the absolute values of a number field. Again, here I can be more explicit, as I was before, and describe exactly how it goes, this correspondence. So where we define the absolute value corresponding to one of those primes appearing there as equal to p, so p is the p, so the restriction to the rationals, of the minus order of x at p, so at this idea that we are fixing. And we have to do something else. So I mean, it's going to give me something equivalent at this thing, but let me divide here by EP. So this is the ramification index that corresponds to the prime. So this gives me a valuation, and this you will see why we need this factor here. Okay, very well. So I mean, a nice consequence of this is the following. is that, for instance, we can characterize the ring of integers of a number field can be characterized by using valuations. So this is the first application that we're going to see about the valuations. By using valuations. So we have that OK is equal to the elements in the field such that the valuation is smaller or equal than 1 for all non-Archimedean valuations. So this, I let you take it as an exercise. So I mean, this is the first application we see about these valuations. So, I mean, the proof. I'm not going to give the proof of this proposition, but I can give you some ideas. If you want to see the proof, you can check the references I'm using. But I mean, how it goes. So I mean, basically, this direction of the bijections, like, is clear. I mean, this is true because it's explicitly given in the statement of the proposition. So if you start with such an embedding, or if you start with such a prime, then you actually get such a valuation here or here. So this is by construction. Actually, what you have to prove is that all periodic valuations actually come from a prime like this, and that all Archimedean evaluations come from an embedding like this. So, well, I mean, you have to play a little bit with this, and I mean, it's not that difficult. But I've been speaking for a long time, and I still want to present you like two main results about those valuations that we are going to prove. Those ones, yes. Okay, so just let me, because I need another proposition before proving the main results that I want to see today with you. And I mean, this one actually is a proposition that, well, comes from this another one. So let me state it. Proposition. So let L equal to K of alpha a finite extension. Let f of t the minimal polynomial of alpha. And I'm going to factor it. So I get something like this. And the question is, where are you factoring? This polynomial is important to precise, because maybe just as a comment. So, I mean, ft, if I look at polynomials with coefficients in k, it is irreducible, right? Because it is a minimal polynomial of alpha. And ft, if I look at its factorization over L, I know that I'm going to find a factor that is actually t minus alpha, right? Because alpha is a root. So, I mean, I'm not factoring f neither in t or in L, in k or in L. I'm factoring it. So, I mean, this factorization I'm writing here. I'm factoring it, and its factorization in kb of t. So basically, I took a valuation on k, and I took the complexion of k for this valuation, and then I see f of t as a polynomial with coefficients on this field. And then I factor. So k of v is an extension of k, which means that I have more elements, which means that this polynomial ft may not be irreducible anymore. So it means that I may have a factorization that looks like this. Okay? So now I'm going to use this factorization to say something. Then, the homomorphism that I define here. So from L to Kg, so it's a homomorphism, a field homomorphism from L, that is the field I'm starting with, into some fields that I'm going to define now. So those fields are, I take the ring, the polynomial ring with coefficients on Kv, but I do the quotient by the G, the corresponding factor J here. So I take this weird thing. So this is a field, right? Okay, so I have those homomorphisms, and those homomorphisms are injective. And moreover, so I mean, this is the funny part, because we still don't see what is this, right? So we want to interpret what's the meaning of this. Moreover, those fields, K of J, or each of them, is the complexion of L. So let me call them actually like this, and I have to specify who is W, the valuation that I have here, with respect to the only absolute value of Kg extending Kb. So, I mean, this, you can see it in a natural way as an extension of this field, because basically you are taking this field and you are adding some element. This is the quotient of adding a variable and doing the quotient by a polynomial. Basically, Kg is Kv, where you have added a root of this polynomial. Okay? So, I mean, this is a finite extension of Kv. So, there is a valuation of Kg that extends the one that you have here, that is V. So, I mean, this is the valuation we are talking about here. And the funny thing is that the absolute values corresponding to different G's are different. And all values and all appear in this way. Okay, oof. So, I mean, this proposition looks like very technical, but I mean, actually it's very good, because it's really giving you the description of all the absolute values when you have an extension precisely given. So, I mean, this was for number fields, right? I just have a number field. And now here, the idea is that I take L, that is just K of alpha, wherever. So basically what I need is a primitive element, if you want, if I'm working with number fields. And we do that, we know that we have them. So we have such a finite extension given by a minimal polynomial, and then the factorization of this minimal polynomial actually tells me about the complexion at the different valuations of the field L, and give me a precise description like this. So, I mean, actually here the proof of this one is in the book, in the second one, in the Bombieri book. You can find the proof of this proposition. I'm not doing it actually because it's easy and boring, if you want. I mean, you just have to check each of the statements that is in the proposition. You just do the computations and you check that all of them are true. But now, I mean, we are going to really use this proposition to prove the first main result that I wanted to prove to you today. So let's see it. So it is called the degree formula, and we are going to use this proposition. So we are going to do some examples later. I mean, in case you start to be a little bit lost with all this notation, don't worry. We'll do an example later and you will see. So I'm going to call it corollary because actually it is a corollary of this proposition. So degree formula. Let L over K be a finite separable extension. Why do I need that finite separable extension? Because basically those are the extensions for which the primitive element theorem holds. And then for those extensions, I know that I can always write L as K of alpha for some alpha. And then I'm in the conditions on the previous proposition. Okay, so I mean, this is why we have this condition here. Then the sum, when W divides B, so those are valuations of L and K, of this degree extension is equal to the degree extension of L over K. So basically, I mean, this means that I may fix the valuation V, right? And I can see on how many different ways I can extend V. So those are the W. So those are all the extensions, all the valuations in L that reduced to V. And then I know that the sum of these degrees, those are finite extensions, actually equals the degree of L over K. So now I can do the proof because it's really a consequence of the previous proposition. So, I mean, the proof is L can be written like this because of the primitive element theorem. We can then apply previous proposition. And just notice that actually, who is this index? Let's go back to the previous proposition. What do we have here? So, I mean, actually, this is L of WV, right? So, basically, we can see this as an extension of this. And what is the degree of this extension? It is actually the degree of this polynomial. So actually what we have is that this degree extension is related with the degree of those polynomials, right? But then what do we have? We have that f the t is equal to this product. So basically the degree of this polynomial is equal to the sum of the degrees of those polynomials, right? That appears here. And which one is the degree of f of t? Is n. That is the degree of alpha. But I mean, n is the degree of alpha, is a I mean, L is equal to k of alpha, which means that the degree of L over k is n. And then we get the equality that we have here, right? So, I mean, this is an easy corollary of the proposition. Okay, so let me write it. So just notice that degree of f of t is equal to n. Okay, very well. So we have this formula. So now I'm going to introduce a little bit more of definition now that I introduced those concepts. So definition. This is going to be called the local degree of B, and is going to be NV equal to the term that appears here that we use. So this is a definition for the local degree. And now with the local degree, I'm going to define the normalized absolute value like this. So, I write it and now we discuss it together. So basically, I took an absolute value that depends on the valuation V, right? And I consider the following normalization that I denote like this with double var. That is the same absolute value, but I take an exponent. Which exponent do I take? I take the local degree corresponding to the valuation. So, you're going to see immediately, because I'm going to state the second main result that I wanted to prove today, why this is important, why it's good to add this exponent. But the thing that I want to say is that actually this is another absolute value, but actually they are equivalent. So, it's not really another one, it's the same one. It is just that I normalize it, right? Because we saw this at the beginning of the course today, that actually two such absolute value are equivalent, they give the same topology, if and only if a relation like this is satisfied, that one is equal to the other to some exponent. So, those two are actually the same one. I'm just normalizing by using this exponent, because one reason, that is a statement of the theorem that I'm going to state now, okay? You will see why. Well, actually, before stating the result, I'm going to give an example, because it's the perfect motivation for the result. You will see why it makes sense to state in this way the result. And well, actually for the example, you are still not going to see the motivation about this normalization, because it happens to be the same thing, but you will see it later. So, example, again, I'm going to look at the rational numbers. And then this holds. I do the product that runs through all the valuations of Q, so Archimedean and non-Archimedean ones, and I do the product. What do I get? 1. So this is an exercise, I let you prove it. But actually it is quite easy, right? Because which ones are the valuations of the rationals? So we have the Archimedean one. The Archimedean one is the classical absolute value that we know. And then we have the p-adic ones. So it's just looking at the order, right? But what is this then? So basically, imagine that x is positive, okay? Then the classical absolute value is just x. But then I have the p-adic ones that is precisely p to minus the order of x and p. So when I do the product of all those valuations, I get x again, but because the minus is dividing. And then I have multiplying x, the absolute value, the classical one. So everything cancels and I get a 1. So this is an exercise for you to write the details. But this is true. And this is easy. So the natural question is this still true when I change Q by another field? And it's not exactly true, because I cannot use our absolute, or it is not true if I use those absolute value, but if I use the normalized ones that I just defined, then it is true. And this is precise, the next result, the second main result that I wanted to see today. So proposition, and this is called the product formula. Let K be a number field. And X an element different from 0. Then the product, when I take all the valuations, Archimedean and non-Archimedean ones, of K is equal to 1. But I have to take the normalized absolute value. So we still have this formula. So I'm going to give the proof, but before giving the proof, just a comment. Actually, I'm stating this result for number fields, but this is more general. Actually, this holds for a larger set of fields. But well, for us it's going to be enough for number fields, so I'm not going to make things more complicated. This is the case, we are going to use it. Okay, let's see the proof. So first, assume the result over the rationals. But well, assuming this is just this, right? That we just check it, or at least the details are left as an exercise, but we already saw it. So we can assume that the result is true over the rationals. We already saw it. Then we proceed as follows. We write this product as follows. I'm going to separate this product for the valuations, how they divide the primes in Q. So I can write the product. So V0 is a valuation over the rationals, and then I consider the B that divides B0, right? So I can partitionate all the valuations here as follows. And then, of course, I have here the same thing, right? But now, because this norm is multiplicative, right? I can write this as the product when V0 is a valuation in Q. And now I'm going to do the product of all of those, okay? But what I'm getting when I do this, actually, this is precisely the norm K over Q of this. Why? Because who is the norm of X as an element of K over Q? This is just the product of all the conjugates of X, right? But all the conjugate of X is precisely the term that appears here, right? It's all the valuation that divides B0. Okay, nice. So I managed to write this like this. But now, look at this. This is a rational number. This is the norm of X, right? This is a rational number, and now in this product, I only have valuations for the rationals. So this is precisely in the setting of the result that we just proved there. Because over the rational numbers, moreover, this normalized absolute value is equal to the absolute value, right? Because there is no extension, so there is no index. So this is precisely equal to this. And then we get the result. Okay, so great. That was the second result I wanted to prove today. I did it. I'm just going to do an example, because I guess that now you are getting crazy with all these different absolute values, normalizations, product formulas, and everything. So I'm just going to finish with an example in which I saw that we have this formula. So example. So I'm going to get K equal to Q of I. Okay? So now we can look at the set of valuations. So let's look first at the Archimedean valuations. So the Archimedean valuations, we know that they are given by the embeddings of Q of I into Q bar. So here we have two embeddings, right? That Q goes to Q always, and I can go to I or minus I. So we have these two embeddings, because the degree of this over Q is 2, so there are two of them. But those two are conjugated ones, right? They are not real ones. So I have to take only one, because I pair up them. They are conjugated one. that was the proposition we saw before. So basically here, I only have one embedding, okay? So I have only one Archimedean absolute value, who is actually the complexion, if you want. The complexion are the complex numbers. So, I can also write this. So, the complexion is equal to C. Okay, very well. So, I mean, this is easy. So, I can write the, well, I mean, again, I did an abuse of notation because, I mean, here tau somehow is the valuation, not the absolute value. Well, it's not a big thing. I mean, if you want here, we can write, that this is equal to, well, is this, right? This is by definition. So by definition, this is equal to this product, so the square root of the product of a number by the conjugate one. So we have this. So we can also compute the normalized one. So which one is the normalized one? So the normalized one is this one, but I have to write an exponent that is actually the degree of the extension, right? So, okay, tau restricted to the rationals is actually the standard absolute value, right? And the complexion is a weird thing of writing it, by the complexion of the rationals with respect to the standard absolute value are the reals. So we can compute the local degree, right? So the local degree, this n tau is equal to k tau q infinite, but I mean this is equal to this degree, so this is equal to 2, right? So the normalized absolute value is equal to this. So it is just the product of the two elements. So I mean, if you want, this is precisely, we can also write it like this, is the norm of x in q of I over q. So we can compute it like this. Okay, so this is about the Archimedean values. So what about the periodic ones? So in this case, depends on the factorization of the prime p in the ring of integers of q of I. But this is kind of classical and we know, right? I mean, there are like 3 cases. So if p is congruent to 3 modulo 4. So if this, you don't know it, I mean, this is an algebraic number theory exercise. It's an exercise for you if you have never seen it before. Otherwise, if you find it very difficult, you can again ask me for a reference if you've never seen something like this. So there are actually 3 cases to consider. Oh, p equal to 2. So I mean, in this case, p is a still prime in q of I. In this case, p is actually equal to the product of 2 primes. And in this case, 2 is equal, as an ideal, if you want, to this ideal to the square. So there is only one factor with some ramification, right? So, I mean, for instance, in the first case, what we get is that x of p, okay, the valuation like this. So we go to the definition. So the definition that we gave in the proposition is that this is equal to the prime that we have here minus the order of p of x, and we have to divide by the, p, because in this case p is still a prime. So we get this, and we have to divide by the ramification index, but there is no ramification in, well, it's equal to 1 in this case. So we just get this. And what about the normalized one? So, I mean, it's this thing, and we have to look at the exponent that we have to put there. So in order to compute the exponent, we have to look at the complexion, right? And I mean, for this, we are going to use the degree formula. And I mean, in the degree formula, it's a pity I erased it. So maybe I can write it here again. So I'm going to write it well. So we have this. No, this is L. Okay, so in our case, L is Q of I and K is Q, so this is equal to 2, okay? there is only one valuation that divides P. B is P in our case, because P is still a prime. So there is only one. So this is a 2, so this degree has to be equal to 2. So this is equal to this. Okay? Now, for those primes that they split as a product of 2 primes, then we have that the associated absolute value is like this, where this is P, so the prime they are lying above, okay, minus the order of x at pi. And there is no ramification in the, well, it's equal to 1, so it's just equal to this. And now the normalized norm is equal to this at some exponent that we are going to compute now. But now look at this. So this is still equal to 2, but here we have 2 terms. We have 2 terms because P is a product of 2 primes like this. And each of them is still at least equal to 1, which means that actually they have to be both equal to 1 to make 1 plus 1 equal to 2. So this exponent this time is a 1. So here we have the different character of both primes, right? And now for prime 2 that we indeed have some ramification, then there is only one prime, and we have to write it like this. Is the order 1 plus I x. At this time the ramification is 2, so we do have to divide by 2 here. And finally, we get that the norm is equal to this norm, and we have to discuss again about the index here, okay? And what do we have with the index there? Actually, if we go to the formula, we are like in the first case, right? Because there is only one prime over 2, so here there is only one term, so it has to be equal to 2. That is what we have there. So this is a 2. So here we have a square. But actually notice that in this case, this 2 is going to cancel with the 2 of the ramification that we have here. So actually we can write this in this way. Sorry that I'm writing it like very small. What I mean is that you can forget about the thing that you are dividing there. So we have this. So now, for instance, it would be nice if you want to do an example to check that we have the product formula as we have here. Okay, so let's do a small example. So let's take, for instance, I don't know, x equal to 2 plus I. If I take x equal to 2 plus I, actually notice that this is equal to 5. So actually the only prime that is dividing x is this one. This is a prime ideal in Q5, right? So basically, if P is different from 2 plus I, then we get that this is equal to 1, because the prime is not dividing. If P is equal to 2 plus I, then what is the norm? So we are in this situation. So basically we get that this is just equal to this, right? And this is just equal, the prime is 5, so is 5, 2 minus the order, by the order is 1, so 5 to the minus 1, right? And now we only have to look at the last one, that is this one. Right, the norm, well, at tau, that is the one at infinity, that we check that is x times the conjugate one, but this is 5. So now we do the product of everything, and this 5 cancels with this 5, and indeed we have proof that the product, when we do the norm of the normalized norms, is equal to 1. So with this, I'm finishing with the examples that I wanted to do. But I invite you to please do a lot of examples with this. Like you can work with the same field because we have done the computations here. So try to play, take a different X, try to compute the norms, try to get familiar with all those concepts. Okay, so this is everything for today. See you in the next lecture. Bye.